So we needed a term of degree 0, we needed a term of degree 1, we needed a term of degree 2, 3, 4, 5, and so on. And then down at the bottom, we're kind of keeping track of the total polynomial that we've come up with so far. So then we started with our function, and then we also had to match up the value of its first derivative, its second derivative, its third derivative. If we wanted to go further, we would need to match up its fourth derivative. We would need to match up its fifth derivative, and so on and so forth. So when I start this process, I like to have all those derivatives down in front of me, so I don't have to worry about calculus. I can just do all the calculus up front, and then worry about algebra. So that once I have all of these derivatives, then I'm just going to evaluate those derivatives at whatever center point I'm looking for. So in our first example, the center point was x equals 0. Let's suppose we now try a different center point, x equals pi over 2. Then I'm going to evaluate each of those derivatives. Instead of at x equals 0, I'm going to evaluate them at x equals pi over 2. And that's going to give me a series of numbers. What's the sine of pi over 2? 1. Cosine of pi over 2? 0. And then minus the sine of pi over 2? Minus the cosine? The sine was 1, the cosine was 0, and so on. So Jessica's point about patterns that we talked about at the beginning of the discussion, it looks like we're kind of seeing a little pattern for this particular function emerging right here. And now here's the key. Here's how we build up these terms of our polynomial. First of all, what was really easy about our first example, p of x equals a plus bx plus cx squared and so on. This was a really nice polynomial to use when x was equal to 0. Because when x was equal to 0, when I plugged 0 into this polynomial, I got a lot of my terms vanishing. If I took the value of this function at x equals 0, all that was left was a. When I took the derivative and then plugged in x equals 0, all I got was the value of b. And so on and so forth. Right? We had a lot of stuff go away when x was equal to 0, when we built up our polynomial out of powers of x. We want the same thing to happen. But when we're at a different starting point, x equals pi over 2, instead of building our polynomial out of powers of x, we're now going to build them out of powers of x minus pi over 2. That way, when I plug in pi over 2, those factors, where they exist, are all going to go away. So instead of powers of x now, we're going to have powers of x minus pi over 2. Plus c times x minus pi over 2, the quantity squared, and so on and so on. So each of these coefficients, when I determine what the coefficient is, each of these coefficients is going to be attached to a power of x minus pi over 2. So x minus pi over 2 to the 0 power is going to be what's attached to the first one. X minus pi over 2 to the first power will be attached to the second one. X minus pi over 2 to the squared will be attached to the n equals 2 term. The n equals 3 term will be x minus pi over 2 cubed, and so on, and so on, and so on. Let's go up to fourth order this time. X minus pi over 2 to the fourth. So that's the second observation, is when we're doing a Taylor instead of a Maclaurin polynomial, the building blocks of that polynomial are powers of x minus the center point. So when the center point is 0, like it was in our first example, they just become powers of x. Here where the center point is pi over 2, they become x minus pi over 2, raised to powers. So that's the second observation. And now the third observation brings all of this together into a formula. So in our first example, when we wanted to match up the second derivatives, we ended up observing that when we took derivatives of our a plus bx plus cx squared plus dx cubed, when I took the third derivative, so triple prime on this, we ended up with 6d. And my question to you is, where'd that 6 come from along the way? What happened that gave us that 6? We took derivatives. And it came from the derivative of the x cubed. The first time we took its derivative, it brought a 3 out front. And then the exponent became a 2. Then the second time we took that derivative, that 2 came out front. And the power became a 1. Then the next time we took the derivative, the 1 came down and the power became a 0. So what did we really get out in the front of my x to the third? We got a 6 because it was 3 times 2 times 1, namely 3 factorial. So there's the reason that we talk about factorial so much last week. This 6 is 3 factorial. Mind equals blown. So let's turn this into a general formula. Supposing that I have a polynomial of whatever order. Whatever order my polynomial is, let's say my polynomial began its life as, let's call it C0 plus C1 times x plus C2 times x squared plus ... And let's say we're all the way up at the nth coefficient and the nth power of x. If I take the derivative of this thing n times, then the first time I take the derivative, this n is going to come out front, and the exponent is going to decrease by 1. The next time I take the derivative, n minus 1 is going to come out, etc., etc., etc. So when I've taken n derivatives of this, I'm going to get c sub n times, in the front, n times n minus 1 times n minus 2 times n minus 3. I'm going to get n factorial. And so the nth derivative of this polynomial, evaluated at x equals 0, in this case, is n factorial times the nth coefficient. But my point is that I want to match that up. In order to make this a Taylor approximation or a Maclaurin approximation, I need to match that up with the nth derivative of the function itself, evaluated at our center point, which in the first example was 0. In this example is going to be pi over 2. But the point is we can solve this equation to figure out what that nth coefficient should be, just by dividing both sides of the equation by n factorial. So the nth coefficient in a Maclaurin or a Taylor approximation, a Taylor polynomial, that nth coefficient is the value of the nth derivative divided by n factorial. That's all there is to it. Where we evaluate that derivative depends on our center point. So if we're building a Maclaurin series, we evaluated them all at 0. In this example, we're building a Taylor series at x equals pi over 2, and so pi over 2 is our center point. So the numerators of these coefficients, the nth derivatives of f evaluated at pi over 2, that's exactly the numbers that we have in the column of green right there. 1, 0, negative 1, 0, 1, 0, and so on and so on. So then all I have to do to turn those numbers into the coefficients for my Taylor polynomial is I have to divide each of them by n factorial. So I'm going to divide the first one by 0 factorial. I'm going to divide the second one by 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, and so on. And those numbers now become the coefficients. By the way, what is 0 factorial? 1. Don't forget 0 factorial is equal to 1, more or less by convention. No, 0 factorial is actually a nice number. The reasons for which are as much historical as they are mathematical. And then I have 0 divided by 1 factorial, 0. Negative 1 divided by 2 factorial, what's 2 factorial? 2. So my third coefficient here, my coefficient of the x minus pi over 2 squared term is negative 1/2. 0 over 3 factorial, well, that's easy. What's 4 factorial? Got that one off the top of your head? 24. 4 times 3 times 2. And there's the coefficient of x minus pi over 2 to the 4th. And then I'll have 0 times x minus pi over 2 to the 5th. And so now I have all the terms of my Taylor polynomial all built up here, which means I can write out now the 4th, or equally well the 5th, order Taylor polynomial for sine of x at x equals pi over 2. My first term is 1 times 1, so that's just 1. My second term is 0, so I don't need it. My third term is minus 1/2 times x minus pi over 2 the quantity squared. My third term has a coefficient of 0, so I don't need it. My fourth term is 1 over 24 times x minus pi over 2 to the fourth. And my fifth term is 0. So this polynomial that we see at the bottom right here is a fourth degree polynomial. It's actually also a fifth degree polynomial if we want to be technical. But it approximates the sign of x better than any other fourth order polynomial can. And so if we were to look at its graph, it would look something very similar to the graph we're seeing on the screen here at the left. And indeed, if we take a look at what the app is telling us about this fourth order polynomial, there it is. 1 over 24 times x minus pi over 2 to the fourth, minus a half times x minus pi over 2 squared, plus 1. Those are the pieces up to fourth order. If we were to keep going, we could get the pieces up to sixth order, seventh order, eighth order, and match up everything that you see there in that formula. So I like this little table as a way of organizing all the information that goes into building a Maclaurin or a Taylor polynomial. All we need are the iterated derivatives of our function, all evaluated at our center point, and then just by dividing those derivatives by the relevant factorials, we get the coefficients that go with the building blocks that make our Taylor polynomials.
So the whole point of this